So let's talk now about the area bounded by parametric curves. So let's suppose, for the sake of this discussion, that we have a parametric curve which obeys the vertical line test. So even if we can't write down an equation to represent this thing as a function, it could be represented as a function. So let's say it starts here and it passes the vertical line test. So this one so this is perfect. So the idea here is that maybe we don't have any way to represent this thing other than by saying this is a parametric curve which is given by some function. I'll kind of mix our notations here just so we can get used to seeing this many different ways. A parametric function r of t where x is given by x of t, y is given by y of t. Okay, and now what we want to do, I mean this is calculus class, right? So what we want to do is we want to try to figure out how can we compute the area bounded below the curve in the x direction, so bounded between the curve and the x-axis. And I'm sure you can guess exactly what we're going to try to do here, right? We're going to chop up our interval into small pieces, the x interval now, and so we chop this up into small pieces, maybe delta xi, and then we try to build some rectangles above this thing. Now what we can do is if we have a point here, say pick what is usually our test point, call this say x of ti star, then go up to the curve, then the height of this is the height of this point up here is given by y of ti star. All right, and then we'll build little rectangles to approximate the area, and of course the area of this rectangle, this is what we'll call delta ai, the change in the area over a small piece. This area is just going to be y at ti star times the width of the base, but that's just delta xi. Okay, and so as we work this out, so we want to take a limit here, obviously. We want to write down a formula for the exact area. So the exact area will be given by, the exact area underneath this curve will be given by the limit as we take our partition here, n goes to infinity, of I from 1 to capital N of this product y of ti with a star times delta xi. But of course this looks just like an integral to us, so that's what we can compute. This becomes the integral where t goes from, let's say, a to b. So the boundaries here are in the parameter space, and I'm being very careful about writing t here because we'll see when we write down the integral, this elongated this s here, right, this part, this corresponds to t values, but the integrand looks like y of t dx. All right, and usually this dx has to match what's over here, and it doesn't right now. Okay, so that's a problem in general, but actually this dx can be written as a differential. So remember, dx dt, we just represent this as x dot of t. This x is a function of t, so its derivative is a function of t. And then just like we would do in regular Calc 1 with dy and dx, we can write down a formula for the differential dx in terms of t. And we can turn this right here into a function of t, and it just becomes the following. So dx as a function of t is equal to x dot of t times dt. All right, and so then of course we just want to plug this into here so that this integral makes sense as an integral of a single variable, an integral of just t. All right, and what we end up with is this formula for the area bounded below a curve. So between the curve and the x-axis, the area is going to be equal to the integral from a to b, where now these are the boundaries in the t direction, but it's going to be obvious when we write the rest of it. It's going to be the integral from a to b of the function y of t times the function x dot of t times dt. So this is the formula for finding the area bounded between the curve and the x-axis. All right, well, one of the benefits to thinking about parametric functions as opposed to just regular Calc 1 functions is that we could try to find the area bounded between the curve and maybe the y-axis instead of the x-axis if we had a reason to. So for this one, let's make sure that this curve passes the horizontal line test. And so if we want to find the area bounded in this direction, all right, so this area right here, the situation is exactly the same. We just turn everything on its side. So we chop up our y interval into pieces now. And so this is like delta yj. And we pick a test point. So we pick a test point right here. And we go over to the curve. And so now the height, quote unquote, from left to right, this is just x of ti with a star. All right. And you can guess what's going to happen. I'm going to leave the details to you guys. But the area bounded between the y-axis and the curve, this is a different shape, right? It's not going to be the same. But this area is given by the integral from c to d. Well, I mean, the a and the b are the same, so I was going to do c and d because it's going in the other direction. But the parameters in the t, for the t, the boundaries of the parameter are going to be the same. And so this is going to be the integral from a to b of x of t times dy, but dy is going to obviously be y dot of t dt. So this is bounded between the y-axis and the curve. All right, it looks very similar. It's not going to give you the same answer, okay? So if you compute this, and then you turn around and you compute this one, these are not the same. So the green area in this picture and the magenta area are not the same. So just be careful. This formula here is for the magenta area. All right. The green area is given by the formula on the